Hey guys, welcome to this intro to separable differential equations. So let's just get right into it. The first thing I want to do is just review what is a basic differential equation. So I have this initial value problem here. You might want to pause the video and just see if you can answer this. Hit play when you're ready. Okay, so the idea behind this is I've got this differential equation here. So basically this is saying that this is the derivative of some function y with respect to x. So I want to figure out what was the original function. So to do that, what I would do is I would take the integral of this with respect to x, and I would get x squared plus 4x plus c since it's an indefinite integral. Okay, so now this is what's known as the general solution. And then I can get to what's known as the particular solution by using this information here. So this is kind of what makes an initial value problem what it is. So what this condition says is if I plug in 0 for x like this, I have nothing to plug in for the c, right? But I know that all of this should equal 3. Therefore, my c will equal 3. That's terrible looking 3. And so now I can get what's known as the particular solution. So remember, this was some function y in terms of x. So this is y of x equals x squared plus 4x plus 3. So that's kind of the basic idea behind differential equations. So you should have a solid understanding of this before you kind of get into this next part with separable differential equations. If you need a more robust view, I do have a video on this. Okay, so here's kind of where I want to go with this. So a differential equation, it could be expressed like this. So this is a little bit different, right? Because if you look at this, this is f of x, y. So this is saying a function that has both x's and y's in it. So how could you think about this? Well, if you know things like implicit differentiation, where you have some equation that has both x's and y's in it, that's what you could kind of think of this maybe as, something similar. Now, this actually can make working with differential equations much harder. And we're actually going to look at a really specific case of this. So this is what's known as the separable differential equations. So we want to think about what would happen if y is a dependent function on x. How could we rewrite this? Okay, so first of all, what does that mean? So if y is dependent on x, that means that y can be rewritten like this in function notation, which would mean that this little differential equation here that I have, I can actually rewrite it like this. So I can rewrite it as, dx of y of x. This equals f of x comma y of x. So this is just another way that we can kind of view this and think about this. Now, there's actually another kind of modification I can make to this, I guess. So we call this equation separable if f of x, y can be alternatively expressed as a product. So if I could rewrite f of x comma y as this function g of x times y, or times h of y, then this would be what I know as a separable equation. So there's kind of a big thing about this. Not all functions can actually be expressed like this, right? So if I were just coming up with a couple of functions that could be written like this, so maybe I could have something like y cubed times 2x plus 3, or I could have something like 5y minus 4, all of this times e to the x plus 2, or maybe I could have something like, I don't know, y to the 6 plus y to the 7th, all of that times 2x plus 1. So notice, so if this color stands for my g of x and this color stands for my h of y, so for my g of x, so here would be my g of x function each time, and then here would be my h of y function each time, right? So you can definitely see how these can be written as a product, but lots of things don't work like this. So if I had something like 3xy squared minus 5x to the 4th y to the 3rd, this is not going to be necessarily separable, right? Or if I had something like e to the xy minus 2y squared times x plus y, again, not going to be separable. So it's when we talk about separable, it's something that has like these really clear factors. And so this is the type of differential equation that we're going to look at. When you have things like this, well, you can take an entire class, you can take classes on differential equations where things start getting kind of crazy like this. So we're looking at a really specific case here. Okay, so going back to this then, how do you actually solve something that is set up like this? Well, in the very nature of this being separable, we actually can break up quite a bit of this. So this dy dx, so if you think back to when you learned about things like differentials, so these two things can actually be broken up. It just kind of depends on what you're using them for, and this is a case where we actually do want to break up kind of this whole thing. So what I'm going to do is I'm going to multiply each side by dx, so that will cancel out. And then at the same time, what I'm going to do, I'm going to multiply each side by 1 over h of y. So 1 over h of y. Okay, so now in doing this, these h's of y's cancel out. So check out what that actually leaves me with them. I'm left with 1 over h of y dy equals g of x dx. And now, a thing that I am allowed to do, I can actually now just integrate each side. So I can then integrate each side. And this right here actually shows you exactly how you will solve then a separable differential equation. And what this allows us to do is this gets a solution of y defined implicitly by x. Okay, so maybe this looks like kind of a lot, but I did want to kind of show you some of the ideas behind this. So let's just jump into an example then. So let's talk about finding the general solution of this. So notice how this side is separable. So I've got this piece here. There's my there's kind of my function of x, and then I've got this other piece here. So basically then what we're going to do is very similar to what I just showed you in this more theoretical example. So we're going to divide out by the y part of the function, and then we're going to bring the dx over to the other side. That's kind of what it looks like that we're doing. So I'm going to go ahead and do that. So this side is going to become 1 over y minus 1 to the 2/3. So I literally divided both sides by y minus 1 to the 2/3. And then this will be dy. And then on the other side, this will be 3x dx, because I brought dx over to the other side. And again, I saw kind of in this way more general example that I was how to actually kind of break that all up. So this was a really nice kind of example to get us started here. So then as far as what do you do next? So it's just then as simple as integrating each side. It's really just comes down to that. So this side, I'm going to think of this as y minus 1 to the negative 2/3, just to help me integrate. But now you just literally integrate each side. So this side will become 3 times y minus 1 to the 1/3. And this side will be 3 over 2x squared. Now you still need a plus c because these are both indefinite integrals. So you just put the plus c on the x side. It kind of doesn't matter where it goes. You just need one c, and that's good enough. So that's kind of the general idea behind this. You really separate each side, and then you can basically integrate each side with respect to its own variable. So let's take a look at one more example. And by the way, I'm just showing you two really basic examples. If you're looking for more examples like this, I do have entire videos of just examples of more problems where you're finding general solutions like this. And then this one's an initial value problem. This whole video is just to kind of give you a really basic intro. Okay, so here's my initial value problem. So take a good look at it. And you'll notice here, so the top part here, this is a function now in terms of x, this is a function in terms of y, so this is definitely separable. So what I would encourage you to do actually is go ahead and separate the two sides to set up the integral, see if you can do that, and then hit play when you think you've got it. Okay, so on this side's going to be 2y squared minus 3 dy, so I'm literally taking this side and basically multiplying it over to this side. And then for the other one, this will be 6 minus 3x dx, and it's because I'm basically multiplying the dx over to this side. So now I've separated everything, so now I can just go ahead and integrate, and this one's not so bad for integrating. So this is 2/3 y to the third minus 3y equals 6x minus 3 over 2x squared plus c. Okay, so just like we did at the beginning of the video, so once again, we're going to use this initial value condition to basically determine what my c has to be. So these two things are going to be connected once again. However, the plot twist here is now you actually have to use both of these numbers to help you solve for c. So I'm going to plug in the 2 for the x's, and then for the y's, so the y of 2 is equal to 3. So for y's, I plug in 3. So this will look like this. So I have 2/3 3 cubed minus 3 times 3 equals 6 times 2 minus 3 halves times 2 squared plus c. And so then you can basically go through and just solve all of that. So this gives me 18 minus 9 equals 12 minus 6 plus c. And then as you go through all of that, you get 3 for c, which means that my particular solution then is going to be, so this whole thing, I'll write it in this orange color just so you can see it. So this will be 2/3 y cubed minus 3y equals 6x minus 3 over 2x squared plus 3. So now I plugged in that c. So that's kind of the basic idea with those And so that will wrap up this particular video. So like I said, I do have other videos where I actually break down more examples if that's what you're looking for, so feel free to check those out. Otherwise, thanks for watching. Feel free to leave me a question or comment below, and I'll see you guys next time.